So welcome everyone, this is exam 1 review session for physics 202. The first thing I want to do is give you the equation for universal gravitation, which is not in this exam review guide, but it's a really easy equation, so it's not a big deal. Universal gravitation, we're talking about universal gravitation when we're talking about things that are like really big, like planets, or they're really far away from each other, like asteroids or planets orbiting each other. And the equation for universal gravitation is simply I call it F big G, is equal to G, capital G, times mass 1 times mass 2 over a distance squared. So the reason why I want to share this is because it's extremely similar to Coulomb's law, which is K Q1 Q2 over R squared, which we'll write in a minute, I'm sure. But this is what it is for universal gravitation. G is a constant. I believe it's 6.67 times 10 to the minus 11th power. Can anyone confirm that or deny that? I'm pretty sure that's right. If it's wrong, then I'm just going to post a correction in the video anyway, so it doesn't matter. Okay. So that's G. Capital G is this value right here. It's the only number I didn't write down for this review. Everything else, I know what I'm doing. And again, it's extremely similar to Coulomb's law. So we're talking about two masses near each other. Radius is R, or really the distance between them, and that's just the force between them. And that's pretty much it for universal gravitation. Now, let's talk about waves, frequency, and wavelength. The first thing we have is wave speed, the wave speed equation. This is simply the equation V equals lambda times F. V is the wave speed. Lambda is your wavelength. And F is your frequency. Next equation, frequency and period. They are simply reciprocals of each other. So in other words, F equals 1 over T and T equals 1 over F, where T is our period. T is our period. F is still frequency. And then the wave equation. You don't always see the wave equation, but when you do, this is what it looks like. Y of x comma t equals A cosine, which can technically be sine as well, but usually we say cosine, of kx minus omega t plus phi, where I now need to explain what all these variables are. K is going to be our wave number. It's called a wave number. And K is equal to 2 pi over lambda, where lambda is our wavelength. I'm going to give you a second to catch up. Now, omega, I don't even know if it has a name, maybe angular frequency, but omega is just equal to 2 pi over t, where t, again, is our period. And then this phi right here, that's the phase shift, we call it, and I really don't think you have to worry about it for this exam. As a matter of fact, I've never seen an exam that has the phase shift in it. It's very rare that it ever shows up. So, but what it's talking about is you literally just, move the sine or cosine curve around. It doesn't even matter for any of the questions, so go figure. Oh, and A is the amplitude. In other words, the maximum height of your wave. And then just a couple constants we need to talk about. The speed of light, that is c equals 3 times 10 to the 8th meters per second. That's an 8. And then the speed of sound is another speed we ought to know. 343 meters per second. Honestly, I don't know if they'll give you these values on the test. I think they will, but just in case they don't, I want to give them to you anyway. And I guess one last thing I do want to say, and I know I ran out of room, but I think your papers, I think it's just right big on this thing here. But see the minus sign here? When they have opposite signs, so like kx is positive, omega t is negative. When you have opposite signs, it means the wave, and I ran out of room, so I need to erase. It means the wave is moving forwards. Wave moving forward. So in other words, if that was the same sign, kx plus omega t, the wave is actually moving backwards, or you'd say to the left. Okay? Is anyone still writing? Okay, then I'm going to move on to the first question. Question 1. You listen to radio station FM 102.3, which has a broadcast frequency of 102.3 megahertz. The waves travel at the speed of light, which we know is 3 times 10 to the 8th. What is the period and wavelength of those waves? So the period is going to be really easy to find. The period is just going to be t equals 1 over f. And I gave us the frequency. The frequency is 102.3 megahertz. What's megahertz? Remember that mega is the prefix for 10 to the 6th power. So that's what I'm going to put there, 10 to the 6th power. And I already plugged this in my calculator earlier. So the answer, I'll just tell you, if you plug this in your calculator, 9.78 times 10 to the negative 9th, and the units for period is seconds. So there's the period, just 1 over the frequency, not too bad. And then if we want to find the wavelength we have to use the wave speed equation, v equals lambda times f. And the reason why we're using this is because we know the v, the speed, it's the speed of light, as we said earlier, 3 times 10 to the 8th is equal to lambda, which is what I'm solving for, times the frequency, 102.3 times 10 to the 6th power. And all you need to do now is divide both sides by 102.3 times 10 to the 6th. When you do that successfully, lambda is going to equal 2.93 meters. So in other words, if you could see these radio waves, I mean the human eye can't see radio waves, but if you could see them, they're 2.93 meters long, which is pretty cool. Any questions on that one? Okay, great. That was an easy one, just in case you're curious. Number 2, the wave equation of a wave on a string can be modeled by the equation y of x comma t equals 2 sine of 3x minus 6t. State the amplitude, wavelength, frequency, and wave speed. We can find all of those things from this wave equation. Also notice I gave you sine instead of cosine. That literally does not matter at all. The easiest thing to find is the amplitude, which is just going to be 2. Amplitude equals 2. Done. I'm not sure if we need units for this. I'm not going to put any units. Wavelength. The way we find wavelength is we need to look at k. Remember the equation is kx minus omega t. That means k is 3 and omega is 6 in this equation. Which means if k is 3 and I know k is equal to 2 pi over my wavelength, well then the wavelength, lambda, is just going to equal 2 pi divided by k if I switch the variables around. And so the answer for wavelength is going to be 2 pi over 3. That is my wavelength, because k is 3. Now to find frequency. Remember that frequency, omega equals 2 pi over t, and we said omega was 6. So 6 equals 2 pi over t. Switch the positions of the t and the 6. T is going to equal 2 pi divided by 6. And remember that frequency is 1 over the period. So I just take the reciprocal of this to find the frequency. And the reciprocal just means flip it. So the frequency is 6 over 2 pi. And yes, that will reduce to a 3 in the numerator. So the frequency is 3 over pi. So I've got the frequency, I have the wavelength, I have the amplitude. The only thing left to find is the wave speed, which, if we remember wave speed, v equals lambda times f again. As we said earlier, lambda was just 2 pi over 3. And frequency is 3 over pi. Looks like a lot of stuff cancels here. The pi cancels, the 3 cancels. Looks like the velocity is just 2. And I guess the units, I'll give the units for velocity because that's just meters per second. But in general, I don't think that units matter for this question. What matters, obviously, is figuring out the different quantities. And that's how you can use the wave equation to figure out all these things. And by the way, if I asked a bonus question for this one, looking at the equation, is this wave moving to the right or the left? Does anyone know? the wave is moving to the right, and that's because it's opposite signs. The 3x is positive, the negative 6t is obviously negative. Opposite signs mean the wave is moving forward, which is to the right. If they had the same sign, it'd be moving to the left. Okay, any questions on number 2? Great. On to the next topic. Next we have standing waves. There's 3 kinds of standing waves we can have. There's the both ends closed, both ends open, and the one end open, one end closed case. For the both ends closed case, the wave diagram is going to look like this, where it has 2 nodes at either end, and the wave goes up and down in the middle like this. If this has some length L, let's say, the equation for wavelength of this case is going to be 2L over n, where remember, n is the harmonic number. It's the number of loops, essentially, you have in your diagram. So in this case, I have 1 loop here. This is the first harmonic, the fundamental frequency, it's also called. And n is going to equal 1, 2, 3, ... Depends on what harmonic you're looking at. It's the harmonic number. N equals harmonic number. Now for the both ends open case, that's going to look like this. Both ends open, the node is in the middle, and the 2 ends end like an open mouth kind of shape. If this is also length L, the equation for lambda is exactly the same, 2L over n. And again, n is equal to 1, 2, 3. It's the harmonic number. You just have to be careful how you count this, because it's still the number of loops. But, I mean, if you look at this, that's 2 half loops. So 2 half loops make 1 full loop. So you count the half loops for the both ends open and make sure it adds to a full loop. And then 1 end open, 1 end closed. This is the only tricky case in the standing waves. And what this would look like is a node on the left and an open mouth on the right. And if this is some length L, this is going to be a different equation. It's going to be lambda equals 4L over n. And that's because n can only be the odd numbers this time. 1, 3, 5, ... You can't have even numbers because with 1 end open, 1 end closed, you need to have an odd number of harmonics here. Any questions on that? Okay, and the only other thing I want to talk about is waves on a string. We have this equation right here. V, again, the wave speed, is equal to the square root of your tension force divided by mu, which is the linear mass density. So Ft is your tension force in the string, and mu is called the linear mass density. And all that is, mu, is equal to the mass of your string divided by the length of your string. That's all it is. And there we go. That's everything we need to know. Keep in mind that we will still be using the wave speed equation, V equals lambda times F, for all of these. That does not go away. We just have some new added fun stuff to talk about. So number 3. A person strums a guitar at its fundamental frequency. The length of the string is 75 centimeters. What is the wavelength? Part 2, if the string is a mass of 5 grams and a tension of 68 newtons, what is the frequency of the tone produced? So the first thing we're going to do is find the wavelength, and it said it's a guitar, which, if we have to think of the guitar as one of these 3 shapes, I think we can both agree it's the both ends closed example, because if you think of how a guitar works, here's the guitar string, and it's being strummed up and down really fast, and it's going to look like this. It looks like the both ends closed example. And this has a length of 75 centimeters, which I will be writing as 0.75 meters. Always convert your units to SI units. And then we can just use the equation, lambda, our wavelength, equals 2L over n. In this case, they're talking about the fundamental frequency. That means that n is equal to 1. So lambda equals 2 times 0.75 divided by 1. And that's just going to be a wavelength of 1.5 meters. There's our wavelength. Now we need to find the frequency of the tone produced. How do we do that? Well, I gave us all this information here, mass of 5 grams, tension 68 newtons. Chances are I'm practically telling you I want to use the tension on a string equation, V equals square root of Ft over mu. Now first we're going to find mu, the linear mass density. Mu is equal to the mass, which we said was 5 grams. I'm not going to write 5 grams, I'm going to write 0.005 kilograms, okay? Divided by the length, which the length is still 0.75 meters. I plug this in my calculator. I'll get 0.00666 repeating, so 0.00667. And I don't even care about the units. I typically only worry about the units for the final answer. So that's going in the denominator right here for mu. Tension, I just told us it's 68 newtons. So that's easy. So then the velocity, the wave speed, is going to be the square root of 68 divided by 0.00667. And that's going to give us a wave speed of about 101 meters per second. Again, that's not my final answer. I want the frequency. But this is great because once I have the wave speed, then V equals lambda times F, the wave speed equation, and 101 equals the wavelength, which we found in part A to be 1.5, times my frequency. I just divide by both sides by 1.5, and I'll get a final frequency of 67.3 hertz. Hertz is the units for frequency. And that's it for number 3. Any questions? Anyone still writing? Okay, good. On to number 4. Number 4. You want the third harmonic of a standing wave to be 400 hertz. Assuming all the wave speeds are identical, which shape will produce this with the shortest length? Both ends closed, both ends open, or one end open and one end closed? This is a great conceptual question. And I think most people would look at a conceptual question like this and just kind of guess. And you might be confident with your answer, but there's no way to really check your work, is there? Well, that's a lie. With any conceptual question like this one, there is always an equation. There is always a law of physics to help guide your thinking. And here's what it is. If we want to produce a wave with a standing wave of 400 hertz, then what we're talking about here is the equation V equals lambda times F. Now, specifically, we want to produce the frequency, but what do we know about those 3 equations for both ends closed, both ends open, and one end open, one end closed? They all have an equation for lambda, right? So in other words, let's solve this equation for lambda. Lambda equals V over F. And here's what we know about this problem. We know that all the waves are traveling at the same speed, they're identical, and all the frequencies have to be 400 hertz. That means all the wavelengths are identical as well. And why is that important? Because not all of the wavelength equations have the same equation. Here's what I mean. Remember that for the both ends closed, the equation is lambda equals 2L over N. For both ends open, the equation is the same, lambda equals 2L over N. And then for the one end closed, one end open, that was the 4L over N. So we know the answer can't be the same for all 3. It's either both ends closed and both ends open because those are identical, or it's one end open, one end closed. And here's what I'm going to do. It said I wanted to produce this sound for the shortest length, right? Shortest length. I'm going to solve each of these for length. The way I do that, I just need to multiply both sides by n and divide by 2. I will get length equals n times lambda over 2. I will get the exact same thing for both ends open, n times lambda over 2, because again I just multiplied by n and divided both sides by 2. And then if I want to solve for the third one, I need to multiply both sides by n, but divide by 4. And like we said before, lambda is the same for all 3. We also know we're talking about the third harmonic, so n is going to be 3 for all three of these. Doesn't even matter because it's going to be the same for all three. The only thing that's different is divided by 2, divided by 2, divided by 4. Hey, that's going to have the biggest denominator. And as we hopefully all know, if you have the biggest denominator, that is going to be the smallest number because you have the biggest denominator. So in other words, the one with the shortest length, it's going to be the one end open case, one end closed, obviously, because it has the biggest denominator. So like I said, whenever you have a conceptual question, there is always an equation that can help prove your answer. Any questions on that one? That was probably the hardest one we've seen so far. Anyone still writing? Okay. Next is number 5. The picture below shows a standing wave pattern for an organ. If the frequency is 1.5 kilohertz, what is the wave speed? So once again, if we want to find wave speed, we have this very nice equation, V equals lambda times F. I give us the frequency, 1.5 kilohertz, which I will convert to just hertz. That's 1500 hertz. You just multiply by 1000. Not too bad. The only thing we don't know is the wavelength. However, we can find the wavelength using the equation, lambda equals 2L over N for the both ends open case. Now, we know the L is 4, L equals 4, but we don't know what N is. Here's my advice to you to find N. All you need to do is say, how many loops do you have? It looks like I have 1 loop, 2 loops, and the 2 half loops gets me to 3. That means N equals 3. Okay, this is the third harmonic, this picture. So that means lambda equals 2 times L is 4 divided by 3. Lambda is just going to be 8/3. I can plug that in my calculator if I wanted to. I don't really care. So then V is equal to lambda times F, which we just said is 8/3 times the frequency, 1500 hertz. My final wave speed, if I plug this in a calculator, I'm going to get 4,000 meters per second. And there's my answer for the wave speed. Not too bad. Not too bad. Any questions on that one? Okay, and that's going to do it for everything waves. We are now on to electric forces and electric fields. The one thing I can not stress enough for electric forces and electric fields, these are two, whenever you see one of these questions, there's really 2 questions it's asking. It's always asking you 2 questions. Number 1, what's the number, like the numerical answer? And 2, we want to know the direction. These are 2 separate questions. I'm going to give you the equations on the left, and on the right I'm going to give you the direction kind of way of thinking. So first we need to talk about the constants. There's 2 constants we need to know. K is equal to 9 times 10 to the 9th. Technically it's 8.99 times 10 to the 9th, but I think it's close enough that we can use 9. And the other constant we need to know is epsilon naught, which is 8.85 times 10 to the minus 12th. Okay, now the equation for force, Coulomb's law. F equals K, absolute value of Q1, absolute value of Q2 over R squared. The reason why I put those absolute value signs is because I do not care if it's positive or negative charge, because all that would tell me is the direction of the force. But we already know which way forces point. Forces, the direction for forces is always the same. Like charges repel each other, opposite charges attract one another. We do not need the positives or negatives because we know this fact. So if anything, if I put a positive and negative charge, that's just going to confuse me in the equation. So whenever I want to figure out the direction, the x hat, y hat, z hat stuff, I'm just going to think it through logically. And as far as the number is concerned, I use this equation. And now for electric fields. Electric field, we have the equation K, absolute value of Q over R squared. There's only one Q in the electric field equation. And again, absolute value there. We'll talk about the direction in a minute, but first the units of the electric field is going to be the Newton per Coulomb. That's an N. I can draw that better. The units are newtons per Coulomb. Oh, and the units for force are obviously newtons. By the way, there is a relationship between electric fields and electric forces. The relationship is the electric field E is equal to your force divided by the absolute value of some charge Q. So if you do have that second charge, you can actually find the equation between force and electric field. And now for electric field lines. The first thing we need to know is that electric field lines will always point away from positive charges and they point towards negative charges. Now let me put like a dividing barrier in between these two, because I'm not saying they're interacting with each other. They're not dipoles, we would say. If they were next to each other, which I'll draw below, if they were next to each other and let's say I had two positive charges, then the positive charges would start going away from each other, but then they have to bend. They have to bend because electric field lines cannot cross. The field lines cannot cross. And so they kind of do this bending shape going on here. And they do that in every direction. They bend away from each other because they do not want to touch. And then if I had two negative charges, it would look like this. Two negative charges. I'm sorry, I didn't want to do two negative charges. It would look exactly the same except the arrows would point the opposite direction. If I had a positive charge on the left and a negative charge on the right, let's say, these do want to bend towards each other because it wants to point away from positive and towards negative. Away from positive towards negative. Away from positive towards negative. You get the picture. They just want to constantly wrap around and touch each other because it's always away from positive and towards negative. Any questions on field lines, direction, anything like that? The last thing I do want to say is I want to talk about the coordinate system. I want to talk about the x hat, y hat, and z hat because there's two ways you can draw it, and the professor does it a different way than I typically like. The way I typically like to do it, I like to say x hat points this way, y hat points this way, and z hat points this way, like out of the page. However, the way your professor does it, I'm pretty sure he does it like this. X hat pointing out of the page, Y hat pointing to the right, and Z hat pointing up. Can anyone confirm which way you typically use, the left way or the right way?
I recognize the right way.
Okay, we will be doing the right way today. Although you can technically do either way because they both work. Okay, thank you. So now, back here, we have number 6. 3 charges are on a line as shown in the figure. What is the net force on the leftmost charge? State the magnitude and direction separately. So for this problem, we're going to use a concept known as superposition. What's superposition? Superposition is a concept that says, hey, let's just look at 2 charges at a time. So since we're focusing on this one, right, we're focusing on the leftmost charge, what I'm going to do is I'm going to first just focus on these 2 charges, and I'm literally going to cover up the other one. And then what I'm going to do is I'm going to cover up the middle charge, and I'm only going to focus on my 2 outer charges. And that's exactly how I'm going to solve this. So let's start by covering up the right charge, and we'll just look at the force between these 2 charges. Now again, the equation for force is K, absolute value Q1, absolute value Q2 over R squared. So that force, I'll call it force 1, equals K, which is 9 times 10 to the 9th, times charge 1, which is 6 nanocoulombs. Remember that nano is 10 to the negative 9th power. Charge 2 is negative 9 times the nanocoulomb. I'm not going to write negative 9 though, because again I use absolute value. So it's 9 times 10 to the negative 9th. Divided by the distance, that distance is 10 centimeters, which I don't care. That's 0.1 meters as far as I'm concerned. Divide by 100. So divided by 0.1 squared. And if I plug this in my calculator, then the first force is going to be 4.86 times 10 to the minus fifth. And again, I don't care about the units, but what I do care about is the direction. Which way do the forces want to go for these two forces, charges? Well, since they're opposite charges, they are going to want to attract one another, but I only care about the left charge because that's the one I'm focusing on. And that arrow is pointing to the right. That is the positive x hat direction. My answer is the positive x hat direction. Okay. Now what I'm going to do is I'm going to cover up the middle charge, and I'm only going to focus on the two outer charges. Okay, and I'm going to call that F2. So F2, very similar. K is 9 times 10 to the ninth. Charge 1 is 6 times 10 to the negative ninth. And then the second charge is 30 times 10 to the minus ninth. And that is all divided by the distance squared. Notice the distance this time, it's the 10 plus 10 centimeters, so 20 centimeters, or 0.2 squared, because it's 0.2 meters or 20 centimeters squared. And if I plug this in my calculator, I'm going to get 4.05 times 10 to the minus fifth. And if I think of the direction here, both of these charges want to repel each other, so they'll point that way. But just like before, I only care about the arrow coming off of my left charge because that's the one I'm talking about. That direction is the negative x hat direction. So here's what I'm going to do. I'm going to write x hat here, but the minus sign goes out in front of the number. Like technically you can write negative x hat here, that's fine, but the reason why I wrote it out in front is because I'm telling myself, hey Dan, you need to subtract these two numbers because this one's positive and this one's negative. And that's exactly what I'm going to do. The final answer is 4.86 times 10 to the negative fifth minus 4.05 times 10 to the minus fifth. And that gives me a final answer of just 8.1 times 10 to the minus sixth. Units are newtons. The direction is positive x hat. And there's my answer. So in other words, the final direction points to the right because we got positive x hat. Any questions on that one? Okay, great. Anyone still writing? Okay, we'll keep going. Next is number 7. When two charges, positive Q and negative Q, are placed a distance d apart from each other, the electric force acting on each is F naught. If you double the charge of both and triple the distance between them, what is the new force in terms of F naught? So I like to call these kinds of problems comparison problems. And they're a very famous type of problem because you've seen them all the time in Physics 1 as well, and they also show up in Physics 2, of course. And whenever you have a comparison problem, here's the goal, or the strategy. The first thing I'm going to do is I'm going to think of the original scenario. I'm going to think of the two charges, plus Q and minus Q, separated a distance d apart from each other. I can even draw that if I wanted to. Here's Q, here's negative Q, they're separated distance d, and they're saying the force there is F naught. Now, I know the equation here. I know the equation in terms of my most basic variables is K, Q, Q, and I know it's negative Q, but remember, absolute value. So I know it's K, Q, Q over the distance d squared. I'm writing everything in terms of my variables. That's exactly what I want to do here. Now, for the second part, when we double both of the charges and triple the distance between them, well, now I've got 2Q here, I've got negative 2Q here, and I've got a distance of 3D. Okay? So now I'm going to say F new, my new force, is equal to K times 2Q times another 2Q, and again I'm making everything positive because of absolute value, divided by 3D squared. This is the most important part of the problem. Make sure the 3D is in parentheses because we need to square both. We need to square the 3 and the D. Now I need to take this to a new page because I ran out of room. So right now we're at the new force is K times 2Q times another 2Q divided by 3d squared. So what I'm saying is, first we can multiply these 2's together. You get 4. The k still out in front. Q over 9d squared, because we square both. Now, look at the coefficients, the 4 over 9. Let's pull that out in front. 4 over 9 times k q over d squared. And the reason why we pull the coefficients out in front is because I'm going to go back to the last page. See right here how we said F naught is k q over d squared, and we have k q over d squared right here? Well, that's F naught. When they tell us to write our answer in terms of F naught, there it is. So the final answer is 4/9 F naught, and we're done. Pretty cool. And yeah, that takes a lot of practice to get as good as I do it, but you can get there if you bother to practice enough. Any questions on that one? Anyone still writing?
Just to make sure, are we going to get the recording?
Yes, I will be sending you a link to the recording after we are done today.
Okay, perfect. Thank you.
Yep, no problem. And also, I think you missed this part, but for magnetic fields, it's not in this review packet, but I'm going to be posting an extra video at after today, probably over the weekend sometime.
Okay, thank you.
Yep, no problem. Next up, number 8. 2 charges lie on the number line as shown. Where should a third charge, negative 2q, be placed so that the net force on the negative 2q charge is 0? Good golly. So this is a tough one. First, we have to figure out even where it goes, because we have 3 options. It can either go to the left, it can go in the middle, or it can go on the right. Here's why it cannot go in the middle. If I put a negative charge here, I don't even care what the value is. If I put a negative charge here, it's going to be repelled away from the negative charge, and it's going to be attracted to the positive charge. 2 arrows pointing to the left. That you will never get a 0 charge there. So in other words, the negative charge must be placed either on the left or on the right. How do I know which side? Remember that this is a tug-of-war game going on right now. In other words, if I consider either of these shapes, let's just consider the left one first, it's going to be attracted to the positive charge, repelled to the negative charge. Same thing's going on in the right case. Repelled from the negative charge, attracted to the positive charge. So we see in both scenarios, we can potentially have a 0 net force. The question is, which tug-of-war game should we use? Should we use the left charge or the right charge? And it almost looks arbitrary. It almost looks like you could use either one, but you can't. And here's why. Let me erase both just for a second. You see how the plus 16 charge is like way stronger? You know what I mean? Like that's a big charge. So in other words, that's like a big kid in the playground. It's going to win that tug-of-war battle. It's going to win the force battle. So what do you do to make it fair? You put the negative charge over here closer to the smaller charge. Put charge closer to smaller charge. And the reason why you do that is because if you want to increase your force, you need a closer distance. You need a smaller distance. This is going to make the tug-of-war game fair. Even though the 16Q is stronger, it's got a bigger force, we're closer to the smaller one. And yes, you need to know that for the test, potentially, if this question shows up. Now the question is just where does it go exactly on our number line? And to do that, we just need to once again use superposition with these charges. Let's cover up the 16Q charge and only focus on the 2 minus charges right now. Yes, they will repel each other. So the force, I'll call it force 1. Force 1 is equal to K. I'm going to leave it in terms of K because as you're going to soon find out, it will cancel out. K, charge 1 is negative Q, which I'm making as positive because again I use absolute values. The negative 2Q is also just positive because of absolute values. Divided by some distance, I'm going to call it x squared. This distance between them I'm calling x. It's the answer to my question actually, is whatever x is. And then force 2, let me now cover up the other charge like this. Force 2 is going to be K times the charge, which is 16Q, times the second charge, which is my negative 2 Coulomb, or negative 2Q, which again I'm making positive, divided by, this is not x squared. Does anyone know what the distance will be?
Would you add them and do x plus 3?
Yes. So what you're saying is this distance is x, and this distance between the two charges is 3. So the total distance is x plus 3. And you're exactly right. So remember that goes in parentheses, x plus 3, quantity squared. And since these forces need to cancel each other out, I can actually set them equal to each other. So what I say is, I'll write it on the next page, I'm saying k times q times 2q over x squared equals k times 16q times 2q over, did I write 3 plus x? I wrote x plus 3, okay. X plus 3 squared. Now look at what cancels. The k cancels, the q cancels, both q's cancel, and you have to be careful because the x's do not cancel because the squared messes us up. So what's left? On the left you have 2 over x squared. On the right you have 32 over x plus 3 squared. And now it comes back to basic algebra. If you want to solve this, you need to cross multiply. So that means 2 times the quantity, x plus 3 squared, equals 32x squared. We need to FOIL this. So it's like 2x plus 3 times x plus 3, which would be 2 times the quantity, x squared plus 6x plus 9. I'm assuming you know how to FOIL. If not, you're really in trouble. I'm not going to lie. Equals 32x squared. And then on the left, we're going to distribute the 2 to both terms. 2x squared plus 12x plus 18 equals 32x squared. This is not an easy one to solve, so I'm going to help us through this one. Chances are you would probably need Pythagorean theorem, but I'm going to subtract 2x squared, subtract 12x, and subtract 18 from both sides so that I get 0 equals 30x squared minus 12x minus 18. Everything here is divisible by 2, so 0 equals 15x squared minus 6x minus 9. I'm going to try factoring this because this does factor, although at this stage you might need to use quadratic formula, honestly, if you can't factor this. So this is going to factor to 15x plus 9 times x minus 1. And if you forget how to factor, you need to think, what are the factors of 9? Your answer choices are 1 and 9, or it's 3 and 3. You have to do the same thing for the 15. Like the 15 has 1 and 15, 3 and 5, and that's it. And then they have to add together to negative 6 in the middle. Now, I already did this earlier, so that's how I was able to get this so fast. But chances are you'd need a little bit of trial and error here, which is why I would probably just say quadratic formula is faster. And what is the quadratic formula? God forbid you need this, but x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And it's good to have that in your back pocket in case you ever need it. So now we get two solutions for x here. We're going to get 15x plus 9 equals 0 and x minus 1 equals 0. We get that from the factors. Now one solution we get is negative 9/15, and the other solution we get is 1. We do not have two answers to this question, we can only have one, and I think it's safe to say that the negative answer cannot be because you cannot have a negative distance. So the answer is x equals 1, but just to be very clear, going back to my number line, x is 1, so it's like 1 away from the 7. You place it at 8. So place, final answer, place the negative 2q charge at 8 meter mark. And that is my final answer. Any questions? Anyone still writing? So now, I'm not going to lie, that's one of the hardest questions in this entire review. And we just did it, so congratulations. The next couple are going to be, I think, on the little faster side in terms of solving them. Number 9, below is the electric field line diagram for 3 charges. The charges have not been labeled. Which of the following are possible values for the charges from left to right? I want you to try this one on your own. I'm going to give you a minute to do it. And just remember that electric field lines always point away from positive and towards negative. So I'm going to give you a minute to do this right now. Okay, I think that's enough time. So first I want to say that since it says which of the following are possible values, I just made up numbers here for the charges. The charges don't actually mean anything. What matters is the positive and the negative. Now, we know for a fact that this left charge has to be positive because all the field lines are pointing away from it. The right charge, for the same reason, has to be positive because all the field lines are pointing away from it. And we know the charge in the middle must be negative because all the field lines are pointing towards it. So the answer choice must be positive, negative, positive. And the only answer choice that has positive, negative, positive is answer choice D. Now, if I did have 2 answer choices, positive, negative, positive, you would have to look at the number of field lines to determine which one's correct. So for instance, if I have like twice as many field lines coming towards the center, well then that would be when, like for instance, -4 coulombs would make sense, when I have double the number of lines heading towards the middle. But I think that's too advanced, honestly. I think it's a little too complicated. I don't think you'll see that. Any questions on that one? Okay. Number 10 is a tricky one, but one related to one I saw in the practice exam. You have a positive charge in the positive x direction, a negative charge in the positive y direction, and a positive charge in the negative z direction. Isn't that confusing? What is the direction of the net electric field at the origin? First thing I'm going to do is draw a picture of this using the notation that you guys use. Here's x hat, here's y hat, here's z hat. So it says I have a positive charge in the positive x direction. Okay, so it's going to look something like this. Positive charge, positive x direction. Then I have a negative charge in the positive y direction. That's going to look something like this. Negative charge in the positive y direction. And then I have a positive charge in the negative z direction. Negative z, since positive z points up, negative z points down. So my positive charge in the negative z direction will look something like this. Now I need to find the direction of the net electric field at the origin, and remember that because of superposition and because of x hat, y hat, and z hat notation, I just need to consider the effect of these 3 charges separately, one at a time. I also know that since electric field lines point away from positive charges, for my first one, in the x hat direction, the field line is going to point that way, away from the charge. And why did I only draw that arrow? Because technically, there's arrows going all over the place away, but why did I only draw this one? It's because I'm looking at the origin, and that's where the field line goes, away from the positive charge, and there's the direction of the origin. So in other words, what way does that point? I would argue that is the negative x hat direction, because if this way is the positive x hat direction, and that's the opposite, must be negative x hat direction. Now onto the y direction. For the y charge here, it's a negative charge. I know the line is going to be pointing towards the negative charge from the origin, and to me that looks like the same direction as the positive y direction. I will say positive y hat. So far I have negative x hat, positive y hat. Let's see if we can get z hat now. So once again, it's going to point away from the positive charge, and it looks like that is pointing up just like the positive z direction. I'm going to say positive z hat. The answer should be negative x hat, positive y hat, positive z hat. Answer choice B is correct. Any questions on that one? I like this question. I think it's a fun, challenging one. You don't have to like it. That's okay. On to number 11. Number 11, what is the direction of the net electric field at point P? This one's pretty simple. Again, we just consider the effect of each charge at point P. So for the positive charge, it's pointing away from the positive charge. For the negative charge, it's pointing towards the positive charge, just like that. And now I need to consider the net electric field. In other words, I have to add these two arrows together. If you remember how to add vectors, you add them tip to tail. What does that mean? It means you start here, our first arrow goes up and to the right, and then the second arrow goes down and to the right. And I would label my start and end points. There's my start point, there's my end point. My resultant vector is just an arrow that goes from start to end. It looks like an arrow that just points to the right. Answer choice C is correct. When you know what you're doing, these questions can be very simple. Any questions on that one? Okay, great. Number 12 is very similar. What is the direction of the net electric field at point P, the center of the square? Once again, I'm going to give you a minute to try this one on your own. It's very similar to the one we just did. You're going to have to consider the 4 charges and their electric fields and then add them together. So I'm going to give you 1 minute and I will reconvene then. Okay, I think that's enough time where you either got the answer or you probably got stuck. So for this one, I consider just all the 4 charges. We'll start with the top left. Points away from the positive charge towards the center. Top right points away from the positive charge towards the center because they're both positive. Bottom left away from the positive charge. And the only one that's different is the negative charge at the bottom. That's going to point towards the negative charge. Now, one thing you may notice is that these 2 charges will cancel each other out. They point opposite in direction and they're the same length. They cancel each other out. Which means the only arrows I have left is down to the left and then another down to the left, which means the final resultant vector is just down and to the left. You can say it's like twice as long as the 2 individual vectors, sure. But that's what the answer is. It's down and to the left. Hopefully that made sense. Maybe you even got it. Any questions on that one? Okay. Number 13, another quick and easy question, if you know what to do. An electron passes through the electric field as shown. Which direction will the electron travel? So first we need to know what electric field lines even mean. Electric field lines, let's write this down, because if you know this, the question is really easy. Electric field lines show which way a proton would move. Electric field lines show which way a proton would move. So in other words, if this was a proton, the arrow would look like this. It would start heading downwards. However, it's an electron, so all it does is move the opposite way. It starts moving upwards, like that. And that's the path the electron would take. Notice it doesn't make a sharp left turn like that. It's gradual, just like that. And that's the answer. Simple as that. Any questions? By the way, I too took this course, not at University of Delaware. I took it at Penn State. This question, number 13, is taken pretty much directly from my exam, which I took, oh God, in like 2016. So, yeah, I'm old. Anyways, oh, one thing I do want to mention. Now is the time to do it. As you can see, I'm wearing my Dan the Tutor shirt. If you get an A in this class, somehow, then you get a free Dan the Tutor t-shirt. Email me after the course is over, and I will send you your free Dan the Tutor t-shirt. I had 4 or 5 students get A's last semester, which is the most ever, so I think it was a good motivator. So if you too want a piece of Dan the Tutor merchandise, you can have it by getting an A in this class. Okay, so if that's not an incentive to get an A, I don't know what is. Number 14. It is known that if you bring a positively charged rod near a faucet of running water, the water will bend towards the positively charged rod. And I'll even draw a picture of that. So like you got your water faucet and water's coming out and you hold a positively charged rod there. Well, what's going to happen is the water is literally going to bend towards the rod. It's like literally going to look like magic. It's pretty cool. Now, what would happen if you brought a negatively charged bar near a faucet of water, would the water attract, repel, or do nothing? This is a great conceptual question, which is honestly, in my opinion, more of a chemistry question. However, since it showed up in the exam for one of them, I looked at the practice exams, this showed up in one of them, I'm going to talk about it. So the answer you're all thinking, or I shouldn't say all thinking, but the answer that makes logical sense is repel, because if it attracted to the positive rod, then it must repel to the negative rod. However, that is not true. It is going to attract. How? I'll explain. Let me just draw it first. It will attract. They both attract, actually. Why? Because like I said, this isn't a physics question. This is a chemistry question. You need to know that water, I cannot deal with this marker. Water is polar. And what does that mean? It means that it aligns its positive, and like water itself has positive and negative charges just by the nature of the H2O molecule. It has a positive dipole and a negative dipole. And so what water does is when you have it with the positively charged rod, it literally arranges itself so it has negative and positive like that, negative and positive molecules like that. Then, when you have the negative charge here, it's just going to rearrange its surface so it's positive, negative, so it still attracts. The water always attracts. And you can even find YouTube videos of it, so I'm not just BSing you here. The answer is it will attract. And how on earth would you know that if you did not know that fact? That's the point. You would have 0% chance of getting the right answer here. So that's why we're talking about it now. Any questions? Okay, great. Gauss's Law, right. Okay, so Gauss's Law is probably one of the hardest concepts on this first exam because most of you don't know what it is or how to use it. The good news is I'm going to explain it right now. Honestly, I don't even know why I grouped this into two different kinds of questions, the 2D surfaces versus 3D surfaces, but I guess the reason why I do, if you have a 2D surface, like number 15 is going to be a 2D surface, then you're probably just going to use the equation flux equals charge enclosed over epsilon naught. That is the equation for flux, which I'll explain in a second. And that is the charge enclosed. The charge enclosed inside of what? The charge enclosed in your Gaussian surface. So then that begs the question, what's a Gaussian surface? A Gaussian surface is an imaginary surface that you enclose your charge in. So you can even look at number 15. You can see I have 3 Gaussian surfaces as identified by the dotted lines. And flux is the electric field that passes through it. Like flux has its own equation. Flux equals an electric field times an area. There's technically a cosine theta in that equation as well, but I'm going to say 99% of the time we don't have to worry about the cosine theta, so I'm not even going to write it. But it's just a measure of how much electric field is flowing through. So if you look at my screen, and let me just go to my screen. If you look, stop presenting, hold on. Sorry about this. Okay, if you look at my screen, and you see I have this circle here. Think of this circle as a Gaussian surface, and imagine I have field lines, which are my finger, going through my Gaussian surface. That's all flux is. Flux is just a field line going through an imaginary surface. Why does it matter so much? Because we're going to use it to find electric fields, and we're going to use it to find electric fluxes. That's the reason why. Okay. Back to the review. So now let's look at And then for 3D surfaces, it's the exact same thing. Flux equals charge enclosed over epsilon naught. However, we can also set it equal to E times A. Technically, you can also do that for 2D surfaces. However, I've never seen a problem in my life that does it for 2D surfaces because it needs to be a 3D surface in order to set it equal to E times A. So that's why number 15 is not going to use the bottom equation. It's only going to use the top one, just so you know. And the same is true for the practice test that you guys took. Like there's a question like this in the practice test that I just stole it from. Number 15. What is the electric flux for each of the three Gaussian surfaces? Each charge represents one Q. Write your answer in terms of Q and epsilon naught. So let's start with A. So all I'm going to say is we want to solve for electric flux. That's Greek letter phi here. And that's going to equal charge enclosed over epsilon naught. So we look at the charges enclosed. It looks like I have negative Q minus another Q plus a positive Q. And that's because I have three charges here. 1, 2, 3. 2 are negative, 1's positive. That's the charge enclosed, divided by epsilon naught. I add them together. My final flux for A is just going to be negative Q over epsilon naught. Yes, flux can be negative, that's fine. And there it is for the first one. Then for B, it's the exact same thing. Flux equals charge enclosed over epsilon naught. This one's even easier. There's only one charge, and it's positive. So the flux for B, we immediately know it. It's Q over epsilon naught. Done. And now all we need to do for C is to look at the Gaussian surface. It has all the charges, including this negative charge down here. So if I count the negative charges, there's 3 negative charges and 2 positive charges. So that means for C, I'm going to say flux equals charge enclosed, which is negative 3Q plus 2Q, so it's 3 negative and 2 positive, divided by epsilon naught. The flux through C is just going to be negative Q over epsilon naught again. And there we go. That's how you find the flux for this problem. Any questions on number 15? Okay, good. The next one's going to be much more challenging. Number 16. Use Gauss's law to find the electric field of an infinite plate of charge with surface charge density sigma at a point 3 meters away from the plate. The first thing I'm going to do is draw this. I'm also going to draw a side view of this, so it's going to look something like this. So this is my infinite plate. It goes on forever, but it's like a side view. So you're looking at like the side view of it. And we want to find the electric field some point over here, 3 meters away. Okay, fair enough. Now, how do I solve this problem? All I'm going to do is Gauss's law. Keep in mind this is a 3D surface. And the reason I know this is because, first of all, we want to find the electric field, and you need the 3D equation if you want to find electric field. Because that's the one where the flux is equal to electric field times the area, which is equal to charge enclosed over epsilon naught. Now I need to think of a shape that I want to choose. Now I actually already made a YouTube video of this. Literally this exact problem. So you can find that on my playlist. And if you don't know what I'm talking about, then just email me and I'll send you the playlist. But anyways, the shape I'm going to choose is a cylinder. It's going to be a cylinder that passes through this infinite plate of charge. And there's my cylinder. And the reason why I choose a cylinder is because if I think of the electric field lines coming off of this plate, remember that it has surface charge density sigma. We don't know what that means exactly, but we know it has a positive charge on it. That's what essentially, as far as you're concerned, that's what it means. This plate has a positive charge like everywhere on it. It's just swimming with positive charges. And as we know, electric field lines point away from positive charges. And so the reason why this matters is because when I consider my flux, I only care about the flux going through this face of my cylinder and this face of my cylinder. I do not care about the sides because no flux, no arrows are going through the sides of my cylinder. So now let's consider the equation. E times A. The area here, it's going to be the area of my blue, just the blue. And the area of the blue is like the faces of a cylinder, which each of those is going to be pi r squared plus another pi r squared, because again, there's two faces. The radius I get to make up. It does not matter. It will cancel. I'm going to choose the radius to be lowercase r, because why not? So what I'm saying is it's going to be the area, which is 2 pi r squared, that's the area of the blue shapes, equals the charge enclosed. This is probably the hardest part of the problem. So the charge enclosed in my Gaussian surface, where is it? I'm going to circle it. The charge enclosed is in the middle. It's in the middle. It's the actual part of the Gaussian surface, my cylinder, that intersects with the positive plate of charge. And that charge enclosed, I don't know what it is. I don't know what it is. I have no idea. Then what do? I use this fact. I know that a surface charge density sigma is equal to a charge over an area. And you can write this down. This is our surface charge density, sigma. Surface charge density. We know the charge Q is going to be our charge. Whoops, I don't know why that happened. Go back, please. Oh no, this is not good. Do I have to really? This is just annoying. If anyone knows a better PDF annotator than Cami, please let me know, because this is very frustrating. Anyways, we know the charge here, the Q, is our charge enclosed, because that's the charge we're talking about. And we know the area is the same pi r squared. I'm just not going to win with this. It's the same pi r squared from, well, not the same one, because that was the blue one, so it's just the red. So in other words, it's not 2 pi r squared, it's just pi r squared, because that's the red area. It is a circle. So that means that my charge enclosed, if I multiply both sides by pi r squared, then Q enclosed is going to equal sigma times pi r squared. That's my charge enclosed. And again, how I did that, I multiplied both sides of the equation by pi r squared. So now charge enclosed in my numerator is sigma pi r squared divided by epsilon naught. Look what cancels here. Pi cancels and the r squared cancels, like I said it would. And all I'm left with is E, my electric field, equals 2 sigma. I think sigma is still in the numerator. Yep. Oh, whoops. I put the 2 on the wrong side. The 2 is technically still on the electric field side. So electric field times 2 equals sigma over epsilon naught. That means electric field equals sigma over 2 epsilon naught. You just divide both sides by 2. And there's my electric field. The cool thing about this electric field equation is that, remember I said that I wanted the electric field 3 meters away from the plate? Well, as you can see, distance never even showed up in the equation. In other words, the distance doesn't matter. The electric field is the same everywhere. Doesn't matter where you are for the infinitely big plate of charge. Okay. Any questions on that one? Now, by the way, there's not many electric field equations I would memorize. I just wouldn't. I would memorize this one, or at least write it down on an equation sheet. Put it on your equation sheet. And again, this is for the infinite sheet of charge. And the reason why I would have it on your equation sheet is because you can have problems like number 17 that use number 16 as the basis, essentially. So here's what I'm saying. Let me erase this. Oh lordy. This is just a mess. Luckily I can take care of this in post. Okay, so number 17. 4 very large plates are lined up side by side. Let me just do that right now. 1, 2, 3, 4. Each plate has a surface charge density of sigma, just like the last problem. What is the magnitude of the electric field in the space between the 2 leftmost plates? So we're talking about the electric field right there. Express your answer in terms of sigma and epsilon naught. So remember that we know the electric field from each of these plates individually. E is going to equal sigma over 2 epsilon naught for any of them. And just like how we talked about earlier in the lesson with superposition, we're going to consider the fact that, hey, if I just think of like one of these individually, I'm going to have field lines going both ways forever. And it's going to be going both ways for all 4 of them. It's going both ways for all 4 of them. And what you need to know is that these arrows, these field lines, are going to add up. So if I consider the space right here, in between the left two plates, look at what I've got here. I've got 1, 2, 3 arrows pointing left and 1 arrow pointing to the right. So in other words, and we know each of these electric fields, each individual electric field is sigma over 2 epsilon naught. So essentially what I have here is the total is -3 sigma over 2 epsilon naught, because 3 are pointing to the left, plus 1 sigma over 2 epsilon naught, because there's 1 pointing to the right. So in other words, I'll get -2 sigma over 2 epsilon naught. The 2's will cancel. And since it asks for the magnitude in the question, always look out for that, by the way. Read the whole question. Magnitude means they don't care if it's negative or positive. They just want the final answer. So I'm going to ignore the negative. And the answer is just sigma over epsilon naught. Isn't that so cool? Now again, if you didn't have that equation, which there's, I think, a chance that it shows up on the test. If you didn't have that equation, you'd have to derive it using Gauss's law in the middle of a problem that's even harder. So don't do that. Just memorize this equation and you'll be fine. Any questions on number 17? Okay, we are on to number 18. We are about halfway through the number of questions, and we're also about halfway through the review. I will be having my 5-minute break around 9 o'clock still. But I think we're having a great time right now. So thank you all for joining me tonight. Number 18. A spherical conducting shell has a +3 Coulomb charge in the center. The conducting shell has a net charge of -2 coulombs. What is the charge on the inner and outer part of the shell? So just so you know, this right here is the conducting shell. It's on the outside. And we're asked to find the charge on the inner and outer part of the shell. This is going to be a Gauss's law problem, and the reason why is because we have a 3-dimensional shape here, because it's a conducting shell. It's 3-dimensional. Oh, it's also spherical, so it's 3-dimensional. So here's what I'm going to say. I'm going to choose 2 Gaussian surfaces so that I can find the charge on the inner and outer part of the shell. The first Gaussian surface I'm going to choose is actually inside the shell itself. So I have to be very careful with these Gaussian field lines. There's my Gaussian surface in red. And that's how I'm going to find the inner shell. How, you ask? Well, we just use the equation. Electric field times the area is equal to the charge enclosed divided by epsilon naught. And the cool thing is, I already know my electric field for this one. The electric field is 0. How do I know it's 0? Because it's a conducting shell. Whenever you have a conductor, remember this fact. Electric field equals 0 inside a conductor. So that's why I chose my Gaussian surface where I did. And if the electric field is 0, then that means the charge enclosed must also equal 0 in order for the math to line up. Now here's the thing. Your charge enclosed encompasses 2 things. Number 1, it has a +3 Coulomb charge in the center. And number 2, it has the inner shell charge. Because that's what I'm solving for, actually. I want to find the charge in the inner and outer part of the shell. So there's 2 charges I have here. The inner shell and the 3 Coulomb charge in the center. So what I'm saying is, since the charge enclosed, the total charge must be 0. That is equal to the inner shell plus 3 coulombs. And so in order to solve for the inner shell, you just subtract 3 from both sides. So that means the inner shell just equals -3 coulombs. And so what that really means is, if I imagine this inner shell as having a bunch of negative charges spread out among the inner part of the shell, well, that total is going to have a charge of -3 coulombs total across the inner part of the shell. And now we still need the outer shell. I actually don't need Gauss's law anymore. And the reason why is because I know the total charge on the conducting shell. The total charge is -2. And I just said the inner is -3. So to find the outer, I just have to put together the simple equation. The equation is -2 coulombs. The total charge on the shell is equal to inner plus outer. And I already know the inner. The inner is -3. So -2 equals -3 plus the outer. And so I just add 3 to both sides. I'm going to get 1 coulomb is the outer part of the shell. And so there we go. The inner part is -3. The outer part is +1. And there we go. This is, I'm going to say it was kind of a Gauss's Law problem. Like, not really. We didn't really use the equation. But this is how we solve it. And it's a good problem to know. Any questions on number 18? Anyone still writing? Okay. Next topic is electric potential and electric potential energy. Pay attention to the equations. V equals K times Q over R. It looks very similar to a lot of the equations we've seen so far today, especially electric field and electric forces. However, notice that the charge Q does not have absolute value signs. That's because for both electric potential and electric potential energy, the direction doesn't matter. The direction doesn't matter. That's great. That means I don't have to worry about X hat or Y hat. It also means that I'm not going to put absolute value signs here. So in other words, if I do have a negative charge somewhere, I do need to write the negative charge, because that does matter. The direction doesn't matter, but the charge does matter. And by the way, we do have a relationship between electric potential, V, and our electric field, and that is delta V equals E times R. What does delta mean? Delta means change in voltage. Change in, I say voltage, it's technically potential, but they're also the same thing. So change in potential is equal to the electric field times the radius or distance, okay? And then the electric potential energy, that is the equation U equals K Q1 Q2 over just R, not R squared, and again the direction doesn't matter. Okay, any questions before we get into the actual problems? Great. Let's look at number 19. A negative 10 volt metal plate is next to a positive 10 volt plate. The plates are 4 millimeters apart from each other. What is the electric field between the plates and which way does it point? So if I have a negative 10 volt plate over here and a positive 10 volt plate over here, and the plates are 4 millimeters away from each other, which I'll convert to meters. That's going to be 0.004 meters because you divide by 1,000. I want to find the electric field between the plates and which way does it point. Okay. So first thing we need to realize is that, hey, we're using the equation that relates voltage or potential. We need to use the equation that relates voltage to electric field times the radius. So change in voltage. Look at this. Change in voltage is going to be, well, it doesn't matter which one you choose first. I'll choose right minus left. So positive 10 minus negative 10. See how I did minus negative 10? Yeah, that's because you do final minus initial. V final minus V initial. It just happens to be a double negative. That makes sense because the total difference between these two is 20 volts, which is what we're going to get here. We're going to get 20 volts. On the right side is the electric field, which is what I'm solving for, and R, like we just said, is 0.004. So in other words, 20, positive 20, is equal to electric field times 0.004. You just divide both sides by 0.004, and we're going to get an electric field of 5,000, and that's newtons per coulomb. And then we still want to find out which way it points. This is the easy part of the question. Electric field always points from, obviously we said positive to negative, But for potential, the electric field's going to point from high to low. And I'll make a note of that. So the answer is points to the left. And then the note I want to write is electric field points from high to low potential. And that's it. We're done. Any questions on number 19? Okay, on to number 20. So number 20 is a question I modified from your practice exam. Fun fact, it was one of the only questions that I actually didn't know the answer to, so I had to look it up. And now I get it. So I think it's a great question, and I think it's the hardest question on this exam packet. So we're going to talk about it. In the figure below, find the magnitude of the electric field and state the direction with an arrow. So the first thing we need to remember is still the same equation from before. Delta V equals E times R. So if we want to find the electric field, we need to find the change in voltage, which obviously all of these lines have the same change in voltage. Delta V is just going to be 5. And R is the hard part. R is hard because you have to use geometry, and like not even fun geometry. Like this is really, really hard. So what I'm going to do is I'm going to make a right triangle here. Look at the right triangle I make right there. As a matter of fact, it's so nice, I'm going to draw it over here, outside of my graph. So the height of my triangle is 2. The length of my triangle is 1, 2, 3. Also, you'll notice that no matter where I drew that triangle, I can draw it here, I can draw it wherever. It's going to have the same dimensions everywhere, which is why this works. So I actually don't want to find the hypotenuse. I don't want to use Pythagorean theorem. And the reason why is because I need to find this distance right there in red, because that's my R. So how do I find that? Well, the first thing I need to do is I need to use SOHCAHTOA to find this angle right there, my angle theta. And it looks to me like this is going to be a tangent because I have the opposite leg and the adjacent leg. So what I'm saying is the tangent of theta, my angle, is equal to the opposite leg 2 over the adjacent leg 3. If I take the arctangent of 2/3, I get my answer for theta. It's 33.7 degrees. Now that's not the answer to my question, but it is going to help me. Let me draw this triangle again now. So theta equals 33.7. Now let me draw this triangle again, but bigger. So what we just found is that this angle is 33.7 degrees. And now that's going to help me find this distance, because notice this distance is at a right angle here. Okay? So now this is great because I have the 3 and the 2 here from before. This is the distance R that I'm solving for, and I'm only focusing on this triangle in blue, which is a right triangle, which means I can still use SOHCAHTOA. However, this time I need to use sine. Why? Because I have the opposite leg, which is R, and I have the hypotenuse now. 3 just turned from the adjacent leg to the hypotenuse, and that's fine because it's a new triangle now. But since I have opposite and hypotenuse, I need to use sine. The sine of 33.7 is equal to the opposite leg R divided by the hypotenuse 3. You just multiply both sides by 3. My distance R, or whatever you want to call it, the distance is going to be 1.66 meters. And that's great because now I can plug that back into my equation. Delta V equals E times R. So delta V, which we said was 5, is equal to the electric field times 1.66. Divide both sides by 1.66. Electric field is going to be 3.00, and the units are newtons per coulomb. And if you want to state the direction of the electric field, then it's easy, because remember that electric field lines always point from high to low. The electric field will point that way, down and to the left. Again, I think that was the hardest problem from your practice exam, because that's really difficult. I don't think you'd probably get that on your own, but now you have a chance. Any questions on number 20? Okay, great. On to 21. 21, find the total electric potential at point A. I don't even think I labeled point A. Point A is like right here in the figure below. Write your answer in terms of R, Q, and K. Okay, that's fine. So if we want to find electric potential, again, we use superposition. We use superposition all the time in physics, electricity and magnetism. And so what that means is you just look at one charge at a time. Let's look at the 6Q charge first. That's the one at the top. The equation for electric potential is V equals KQ over R. Notice they want my variables in terms of, R, Q, and K here. So all I need to modify with this equation is my charge, because my charge is 6Q. So 6Q goes in the numerator. That's it. We're done that potential. Next potential we'll do is the -4 coulombs. That points to the right. So for the -4 coulomb charge, we cannot ignore the negative. We cannot ignore the negative. V equals K times Q is -4Q over R. That distance is the same. It's still R. And that's it. Don't we love it when the direction doesn't matter? Because if this was forces or fields, I would have to be talking about X hat and Y hat right now. And I don't have to do that because I don't care about the direction. So that's why electric potential is nice, and why if this was forces or fields, again, you need to pay attention to the X hat and Y hat notation. You need to. Super important. And then the last one is the +3Q. But as you can see, it's at a 40-degree angle. I've got good news for you. That 40-degree angle does not matter. The direction doesn't matter. Direction doesn't matter. All that matters is the charges. So for the +3Q charge, the voltage is going to be K times +3Q divided by R, and there we go. And now I just need to add these three potentials together to get my total. It's going to be 6Q minus 4Q plus 3Q. Let's see what that is. 6Q minus 4Q plus 3Q. That's going to be 5Q as my total. So the final answer, V total, the total electric potential is K times 5Q over R. And there we go. Isn't that nice? Any questions on that one? Anyone still writing? Okay. And with that, we move on to the next topic, which is capacitance and resistance. We're getting very close to DC circuits now, which, by the way, DC circuits is my favorite part of this course. I don't really like this part that we're doing right now, but it's important, so we talk about it. So we have two equations for capacitance. The first equation is C equals Q over V, and what this means is your capacitance, which is C, is equal to Q, which is the amount of charge you have on your plates, divided by V, which is your potential. You can also say voltage. That's also the voltage. It's the same thing. Electric potential and voltage are the same thing. And then the second equation we have for capacitance is C equals epsilon naught A area divided by D, the distance between the plates. So just so you know, capacitors are literally just two plates like this, separated some distance D away from each other. That's all a capacitor is. If you want to make a really poor capacitor, then put your hands together and you just made a capacitor. Congratulations. It doesn't really do anything because your hands don't really, store charge, we'll say. But you could theoretically do that. We're really talking about metals when we talk about capacitance. And then we have an equation for a dielectric. Now, what's a dielectric? So here's my capacitor right here. Go back to this one. What's in the middle of the capacitor? It's air, right? There's nothing in the middle. It's just air. Well, if you do put something in your capacitor, almost think of it like a jello in the middle. or a piece of glass, or a piece of plastic, or a piece of wood, or a piece of water, whatever you put in there, it's going to have a dielectric constant K. And our equation for the new, I call it C new, your new capacitance is equal to K, your dielectric constant is what it's called, times your original capacitance. So the new capacitance is equal to K times your original. And there we go. And then for resistance, resistance has its own equation. R equals rho L over A. That is not P. If you ever say P, I will correct you. That is Greek letter rho. It looks curvy, and that's it. Now, rho is called the resistivity. What the heck is resistivity? It's saying how resistive is your metal. So in other words, if you have something like, let's say, copper. Copper has a very low resistivity. Why? Because resistance means it resists. And copper doesn't resist. Copper likes to flow. Stainless steel is another example. Stainless steel has a low resistivity. That's why you don't stick a fork in a toaster, because you're going to electrocute yourself. Why? Because it has very low resistivity. It likes to conduct. You're going to shock yourself. So in general, metals have very low resistivities. Other things like plastics, woods, anything that's an insulator, we would say, has a very high resistivity, which is why they make resistors out of plastic, just so you know. L is the length, and A is, again, your area. So that's really it for resistance and capacitance. Now let's look at some problems. Number 22. Two square plates, both with side lengths of 13 centimeters, separated a distance of 10 millimeters, form a capacitor. If the electric potential difference between them is 100 volts, what is the charge on each plate? What is the energy stored in the capacitor? So for this one, I'm going to draw a picture. I've got two square plates separated a distance away from each other, and they're hooked up to some kind of battery, let's say, that has 100 volts on it. Now, both of these capacitors are squares, so if we want to find the area, A, it's going to be the side length squared, because that's the equation for area of a square, side length squared. Each side length is 13 centimeters, so that's going to be, I need to convert to meters, as always, so it's going to be 0.13 squared, which, if I plug that in my calculator, is 0.0169. Okay, so I've got my area now. The distance between them is 10 millimeters. Divide that by 1,000 to get 0.01 meters. That's how separated they are. And now I want to find the charge on each plate. So for that, we're going to use the equation C equals Q over V to find the charge. We've got a problem, though, because we know the voltage, 100, but we don't know the capacitance. That's why we need to compute it using the second equation for capacitance, C equals epsilon naught A over D. Now, luckily, we know all the variables here. Epsilon naught is just a constant, 8.85 times 10 to the minus 12th. Area, we just found it, it's 0.0169. And D, the distance, we just said is 0.01 meters. If you plug that all in a calculator, you're going to get a capacitance of C equals 1.50 times 10 to the minus 11th. And now we just need to plug that in the equation C equals Q over V. So 1.50 times 10 to the minus 11th equals charge Q divided by 100. If you want to solve for Q, just multiply by 100. We'll get a charge Q of 1.50 times 10 to the minus 9th. And the units for charge are coulombs. A lot of people forget that. So coulombs is our answer there. And if we want to find the energy now, the energy is going to be U equals 1/2 CV squared. Or there's a second equation for energy, 1/2 just Q times V. Both work. You can use whichever one you want. Since we just found the charge, let's use the second one. Energy equals 1/2 times 1.50 times 10 to the minus 9th times the voltage, which is 100. It looks like I'm going to get an energy of 7.48 times 10 to the minus 8th and the units for energy are still joules, just like they were in Physics 1. Any questions on number 22? Okay. Next, number 23. A parallel plate capacitor has a capacitance of C0. When a thin sheet of glass is placed between the plates, K equals 5.6, the capacitance increases to 67.2 microfarads. What is the value of C0? So again, this is almost, I don't think it's a comparison problem necessarily, but we're going to treat it like a comparison problem. And what does that mean? It just means that first we're going to say the equation with the capacitance in it. It's the new capacitance is equal to K times your original capacitance. We're excuse me. We are solving for the original capacitance, which was C0. We are solving for that. The new capacitance, they tell us, is 67.2 microfarads. So that's going to be 67.2 times 10 to the minus 6. Don't forget the 10 to the minus 6 because micro means 10 to the minus 6 equals K, which is 5.6 times C0. All you need to do here is divide both sides by 5.6 and you'll get the original C0 capacitance of 1.2 times 10 to the minus 5th farads. And in case you wanted to convert that to microfarads, because we can do that, you would just have to take your answer, which was 1.2 times 10 to the minus 5th, and you would just multiply that by 1 times 10 to the negative 6th farads in 1 microfarad. There's the conversion factor. And if you plug this in your calculator, you would get just 12 microfarads. So that's another answer if you want to do it that way as well. Any questions on 23? Okay, on to number 24. Number 24, this is a comparison problem. Two resistors, resistor A and resistor B, are made of identical materials. Resistor A is twice as long as resistor B, but resistor B is twice the diameter of resistor A. What is the ratio of the resistances RA over RB? So the first thing I want to say for this one is some of the things that they're telling us right from the get-go. They're saying they're made of identical materials. What they're really saying is the resistivity is the same. Rho A equals rho B. The next thing they're saying is resistor A is twice as long as resistor B. Translation, the length of A is twice the length of B. And then the final thing they say is that resistor B is twice the diameter of resistor A. I don't want to say diameter, I want to say radius, because the equation that we're going to use here for these wires is pi r squared. That is going to be the area. And by the way, if you didn't know that, the reason why is because what are wires at the end of the day? If you look at a wire really close up, it's just a really small cylinder. And remember that the area in the equation is not the area of a cylinder, it's the cross-sectional area. So in other words, if I take a slice, a little slice out of my cylinder there, that shape right there is a circle, which has the equation pi r squared. So long story short, I want pi r squared as my area, but the problem is they said diameter. The good news is, what does diameter equal? Well, diameter equals twice the radius. So in other words, if you double the diameter, you're also doubling the radius. Like these two are like interlocked with each other. What I'm trying to say is, if resistor B is twice the diameter of resistor A, then I'm going to say RB equals 2RA. It's double. That's all I'm saying. And now I need to find resistance RA and RB. So resistance RA, we're going to use the resistance equation, which is rho L over A, which again, the area is pi r squared, like I said. I'm also going to replace all of these variables with the A subscript here because I'm saying that all of these belong to A. We would then do the exact same thing with B, by the way. RB is going to equal rho B LB over pi RB squared. And this is the reason why I wrote this, and I wrote this, because now I'm going to be plugging in to both of those equations. Now, I don't have to plug into both. I only have to plug into one. Since it doesn't matter, I'll choose B. But what that means is I need all three of these in terms of B. Like, this one's good because it's in terms of rho B equals. This one's good because it's in RB equals. This one's not good because it's in terms of LA equals. What am I saying? I'm saying I just have to divide both sides by 2. So LB equals 1/2 LA. And now I can plug in all three of those variables into RB. So let me show you what I'm talking about. I'm saying RB equals, you don't have to write this, I'm just rewriting it. RB equals rho B LB over pi RB squared. So what I'm saying is, I can rewrite this as rho A, because that was identical, times 1/2 LA, because that's what LB equaled, divided by pi times the quantity, need to put this in parentheses, 2RA quantity squared. There's a very good reason why I'm doing this, but first I'm going to simplify. So this is pulling this 1/2 out in front. I've got 1/2 rho A LA divided by 2 squared is 4, so 4 pi RA squared. And yes, we can reduce the 1/2 and the 4. That's going to reduce to an 8 in the denominator, so it's really like 1/8 rho A LA over pi RA squared. And the reason why we did this is because the question was asking for what? The question was asking for the ratio of RA over RB. Look at what I've got going on here. For RA, it was rho A LA over pi RA squared. And for the denominator, it's what we just wrote right here because this was RB. So I'm dividing by 1/8 rho A LA over pi RA squared. Now at this point, maybe you see some things cancel out. I'm not going to cancel them out just yet. What I'm going to do instead is say this is a complex fraction. Whenever you want to deal with complex fractions, multiply by the reciprocal. So all I'm saying is I'm going to rewrite it like this. Rho A LA over pi RA squared times the reciprocal. Flip it. 8 over 1 times pi RA squared divided by rho A LA. Now I'm going to cancel out like everything. Rho A cancels, LA cancels, RA squared cancels, and pi cancels because everything's in terms of A. And all you're left with is 8 over 1. The answer is just 8. That is the ratio of RA over RB. And in case you're wondering what this means in English, all this means is that RA is 8 times higher than RB. Resistance A is 8 times higher than resistance B. Pretty cool. Any questions on 24? Okay, we're going to do number 25 and then we're going to take a 5-minute break. So, number 25. A resistor's normal resistance value is 100 ohms. What will be the new resistance if you reduce the length and radius each by a factor of 4? Okay, so this one's very similar. Again, it's a comparison problem. So first we're going to write the original resistance. R equals rho L over pi R squared again. And again, well not again, but this is equal to 100 ohms. They tell us that right here. Now for my new one, our new I'll call it, I reduce the length and the radius each by a factor of 4. So that means rho didn't change again. Length is now 1/4 L. And pi R squared is now 1/4 R quantity squared. Now since it's 1/4 quantity squared, I do need to reduce that. it's going to be, first pulling the 1/4 out in front, 1/4 rho L divided by 1/4 squared is 1/16 pi r squared. And now here's what I'm going to do this time. This time I'm going to say, hey, rho L over pi r squared equals 100, right? And I see those variables right here. So in other words, that right there I'm going to replace with 100. That is the strategy. So then what am I left with? I'm left with numerator 1/4, denominator 1/16 times 100. And now all I need to do is multiply by the reciprocal like we did before. 1/4 times the reciprocal, 16 over 1, still times 100. The answer for my new resistance is 400 ohms. You see, comparison problems aren't that bad when you know what you're doing. So now we will be taking a 5-minute break. So go to the bathroom, do whatever you need to do. We will be continuing at 9 o'clock exactly. Okay, let's get started again. So we still have, I think, about 10 questions to go. I got an hour left. Honestly, I'm pacing this perfect. I'm really happy with myself. We're going to end probably right at 10 o'clock. So with the next topic, we have capacitors in series and parallel. And then after that, we're going to get to resistors. But first, capacitors, which are the opposite of resistors in terms of the math. So the first thing we're going to say is, this is what capacitors in series looks like, which you probably already knew. But they're just in a straight line. Whenever I think of series, I always think of cars going down a road. In this case, there's only one road that they can go down, so that's why they're in series. Now, the logic for how we add them is strange for series with capacitors. You do this reciprocal logic. 1 over C total equals 1 over C1 plus 1 over C2. That's how you find the total capacitance. Now, what's interesting is when they're in series that the charge Q is the same for all of them. So what I'm saying is Q1 equals Q2 for the two capacitors in series. Same charge. However, what's different is the voltage. The voltage is V, we would say they sum. And all I mean by that is like the total voltage is equal to V1 plus V2. Now, capacitors in parallel is the exact opposite. This is what capacitors in parallel look like. Again, whenever I think of parallel, I think of a car coming across a fork in the road, and there's two paths the car can go down. It's exactly what I think about. And for this one, this is easy for capacitors. Capacitors love being in parallel because you just add them directly. No funky math involved at all. However, what's interesting is that the exact things I just said about the charge and the voltage, they switch. So in other words, the charge is Q, they sum. So in other words, Q total is equal to Q1 plus Q2. And the voltages are the same. So in other words, V1 equals V2. Okay? And with that, we're ready to go on to number 26. Number 26, we want to find the equivalent capacitance of the circuit. The trick to combining capacitors is a lot of times they're in a combination of series and parallel. These capacitors are in both parallel and series. Specifically, these two are in parallel and the other one is in series. And because of that, you can't add them all up at the same time. You have to add two of them first. In this case, we're going to add the parallel first. You have to. They're connected in parallel before they're connected in series. And since they're connected in parallel, we love it because C total is just 1 plus 2. You just add them together. You're going to get a total capacitance of 3. Now here's a question. Should I have converted them first to farads? Because I see micro there. Should I multiply by 10 to the minus 6th? No, you don't have to for this, because all the units are going to be the same, microfarads. Like our final answer is going to be in microfarads. The only time I would ever convert to farads is if I was using another equation like the RC circuit equation, which we'll see at the end of this review. And then I like to redraw the circuit. So when I redraw the circuit, what I've got here is now two capacitors in series, the 3 microfarad and the 4 microfarad. And since they're in series, we have to do the not fun stuff. 1 over C total equals 1 over 3 plus 1 over 4. Now the trick to adding these is you just need a common denominator. In this case, the common denominator will be 12. So I multiply 1/3 by 4 over 4. That gets me 4/12. I multiply 1/4 by 3 over 3. That gets me 3/12. And it looks like the total is 7/12. But that's not the total. Because remember, that was 1 over C total. So if I really want the total capacitance, I just need to flip it, take the reciprocal. The answer is 12/7 microfarads, because I had to take the reciprocal. And I know I can convert that to a decimal. I really don't care. Any questions?
I have a quick question.
Yep.
So whenever the question's asking for equivalent capacitance, it's just asking for the total capacitance?
That's right.
Okay, thank you.
On to 27. 27, same thing, but much more difficult. If C1 equals 1 farad and C2 equals 2 farads, and you see a bunch of C1s and C2s going on here, what is the equivalent capacitance of the circuit? So I think the biggest thing you could do wrong with this one is just jump head first and start solving without any attack plan. The first thing you should do is ask yourself which capacitors are in series, which ones are in parallel, and the way we do that is I'm going to be the car driving down this road. I'm going to start at point A, okay? I'm driving down, I come across C1, there's only one road, C1 is in series. Great. And then I get to here, look, a fork in the road. I can take two paths. C2, which is in parallel, because again, fork in the road. Or I can go down this other path, and the thing about the other path is that's got 3 resistors on it in series. So yes, these 3 resistors are in both series and parallel, but first they're in series before they're in parallel. And then the roads finally meet up at this point right here. And after they meet up, really? Can't pick a color? There we go. After they meet up right here, they continue back this way, where C1 here is in series again. So now we have a lot of adding to do. And the order, again, matters. The order is I need to add the green first, the green series first. Then I'm going to add the blue in parallel. Then I'm going to add the other ones in series. Okay? So let's do the first one first. These 3 in series. Since they're in series, that stinks. So 1 over C total equals 1 over C1, which is 1, plus 1 over C2, which is 2, plus 1 over C1, which again is 1. I get a common denominator here of 2. This is really 2 halves plus 1 half plus 2 halves, which gives me a total of 5 halves. And again, that's 1 over C total. So really, C total is the reciprocal of that, which is 2/5. So now I'm going to redraw my circuit. So I've got all 3 of those capacitors just simplified to a single capacitor like that. And I've still got all these capacitors here. But the next one I'm adding is the 2 here, the C2, which is 2 farads, and this 2/5 right here. And since they're in parallel, well, that's easy because the total is just the 2 added together. So 2 plus 2/5. And this has a common denominator of 5. So that's really like 10/5 plus 2/5, which is equal to 12/5. And do I take the reciprocal of that? Nope, because these were in parallel and they just add directly. Okay. So now we're getting to the final push. We now have, I'm going to draw the circuit one more time. We have capacitor here, capacitor here, capacitor here. These two are both 1 farad at the top and the bottom. This one here we just said was 12/5 farad. And the 3 of these are in series, which means one more time we have to do that annoying logic. 1 over C total equals 1 over 1 plus, I'm not going to write 1 over 12/5 because that just looks ridiculous. Instead, just take the reciprocal, write 5/12, much better, plus 1 over 1. Again, I need a common denominator. By the way, if you wanted to plug this in your calculator, you could. I don't need it, so I'm not going to write it with the calculator. So 12 over 12 plus 5 over 12 plus 12 over 12. 12 plus 5 is 17. 17 plus 12 is 29. 29/12. Remember, that's not your final answer. That's 1 over C total. So the final answer is the reciprocal of this. C total equals 12 over 29. And the units this time are farads. And there we go. That's it for 27. A lot of redrawing the circuit, a lot of combining. Any questions? Okay, and now we're on to DC circuits. My favorite part of the course, honestly. I love DC circuits. I'm an electrical engineering major. I graduated with that degree in 2019 at Penn State. I'm barely qualified enough to screw in a light bulb, but this stuff is really fun and I do enjoy it. So the first thing we're going to talk about is Ohm's Law, which is the most important equation in all of DC circuits, which is V equals I times R. There's 2 ways we can do this. One is you can do Ohm's Law for the whole circuit. That's where you condense the whole circuit into 1 resistor and 1 battery, which we do a lot. We usually do this first. And then after that, we look at the individual resistors. Not the whole circuit, just the individual resistors we look at for Ohm's Law. Now power. Power has a few different equations. Power equals V times I, voltage times current. Power, if you plug in V equals I times R, with Ohm's Law, you actually get 2 different versions of this equation. You can also get I squared times R, I squared times R, and the third equation you can get is power equals V squared over R, voltage squared over R. So depending on what variables we have, sometimes it's easier to use one of these 3, depending. Okay, now resistors in series and resistors in parallel. I'm not even going to draw the picture because it looks exactly the same as it does for capacitors. But R total in series, this is the one we like now. Notice it's the opposite as capacitors. Opposite as capacitors with the series and the parallel stuff. Now, the current in series is going to be the same, and the voltage is going to sum when they're in series. So the currents are the same. That's because, again, there's 1 road. The current only has 1 road to go down, so it has to be the same. Voltages will sum. Now for resistors in parallel, this is where we have the reciprocal logic. 1 over R total equals 1 over R1 plus 1 over R2. And likewise, it's going to be the exact opposite. The currents are going to sum, and the voltages are going to be the same. I would highly recommend memorizing these things in the boxes that we just wrote. I would definitely memorize that and put it on an equation sheet. Now, KCL, Kirchhoff's current law. This simply says that the current going in must equal the current going out. So in other words, if I quick draw up an example, and I have three currents here. Let's call them I1, I2, and I3. Then all the currents going in, which is I1, must equal the currents going out, which is I2 plus I3. And that's how you use KCL, Kirchhoff's current law. Then Kirchhoff's voltage law, this one's the complicated one. I wouldn't even use it that often, but sigma V equals 0. Remember, sigma means summation. If you add all the voltages together in a loop, you get 0. So sigma V equals 0 for a loop. Let me show you what I mean by a loop. Because at the end of the day, circuits are just a bunch of loops with resistors in the middle of them. So for example, if I have this right here, and this is some resistance R, and this is some battery V, and this is some current I, let's say, you pick a starting point. I'll choose to start here. That makes the most sense. Whenever I come across a battery, that's positive. It's like going up an escalator. And then whenever I hit a resistor, I subtract it because you're going down. Now, the voltage in that resistor, V equals I times R, Ohm's law. So I'm going to say minus I times R. And that is equal to 0. And that's it. All the voltages must sum up to 0. So whenever you hit a battery, it's positive. Whenever you hit a resistor, it's negative. Okay. So now let's look at some examples. Number 28. The voltage at point A is 20 volts and the voltage at point B is 15 volts. If the current through the resistor is 50 milliamps, what is the value of the resistor? So notice 20 volts at point A, 15 volts at point B. One thing I do want to say about Ohm's law, I kind of lied a second ago, V equals I times R. Technically, it's delta V. I don't write the delta because it's usually tedious, but in this case it's important. And the reason why it's important is because it's always the final minus initial. It's going to be, in this case, 20 minus 15. If you want to, you can write 15 minus 20. It doesn't matter. You'll get a negative value for the current. But just remember that what we said earlier about electric fields flowing from high to low. Well, same thing for current. Current is going to flow from high to low. It always does. Current always flows from high voltage to low voltage. And so 20 minus 15 is going to equal I times R. The resistor I don't know. I do know the current is 50 milliamps, which I need to convert to amps, which is 0.05 amps for the current. So plugging in here, 20 minus 15 is 5, equals the current, which is 0.05, times the resistance R. Divide both sides by 0.05, and we'll get a final resistance of 100 ohms. And there we go. Any questions on 28?
So is Ohm's law always delta V?
I'm going to say yes, and I'm also going to say that most of the time you don't need the delta.
Okay.
And the reason why is because usually it's minus 0. Like in this case it was 20 minus 15. Usually it's like 20 minus 0, so you don't need the delta. You know what I mean?
Okay, so because usually the negative electrode is 0, right?
Yes, exactly.
Okay. Okay, thank you.
Now we're going to look at some problems today where we do need to use delta V, and I'll help us through those ones. Don't worry. Okay, number 29. What is the voltage and the current through each resistor? How much power does the circuit draw? So real quick, I want to talk about strategy for DC circuits, because there is a strategy. It's not just wing it. Although my students can certainly try. Step 1, we are going to combine to a single resistor. Combine to single resistor. Just like we did earlier with the capacitors, we're going to do the same thing with resistors. And in this case, we have 3 resistors, and it looks like they're all in series. So all 3 of them are in series, so that's not going to be too bad. Step 2, we need to find the current next to the battery. And the way we do that is by using Ohm's law. So we need to find the current in the battery. And we can't do that until we have a single resistor, by the way. Step 3, we're going to use Ohm's law. And again, like we said before, we have Ohm's law for the individual resistors in the whole circuit. Step 3, Ohm's law for individual resistors. For the individual resistors. And in this case, we have 3 individual resistors, so we're going to use that 3 times. Okay, so this problem is actually not so bad. I can combine the 3 of them in series, which again, for resistors, that's the easy one. So the total resistance is just equal to the 3 numbers added together. It's going to be 10 plus 12 plus 20. And that's going to be a total of 42 ohms. Okay. Now I'm going to redraw the circuit. I love redrawing the circuit because it really helps guide me what I'm doing. So that's 42 ohms. This is still a 6-volt battery. And now I need to find the current. This is step 2. The way we find that current, I, is you just use Ohm's law for the whole circuit. V equals I times R. Now voltage is 6. Current is what we're solving for. And the resistance is 42. So you just need to divide 42, and you're going to get a current of, I wrote it as a fraction. You can write as a decimal. It really doesn't matter. But I got 1/7 amps. Okay. So there's my current. And now, remember this. Remember how we said that for series, the current is the same? That means the current through all 3 of these resistors is 1/7 amp. So we're like halfway done the question now, because we want to find the voltage and the current through each resistor. We have the current through each resistor. It's 1/7 amp for all 3 of them. And now, if you want to find the voltage across any of them or all 3 of them, then you just use Ohm's law. V equals I times R. And again, this is one of those times where I'm not going to say delta. I'm just going to write V. So V, we're going to start with the 10 ohm resistor. It's going to be 1/7 times the resistance is 10 ohms. You're just going to get 10/7 volts. And again, that's it for the 10 ohm resistor. For the 12 ohm resistor, it's going to be the exact same thing, except now it's V equals 1/7 times 12. So you get 12/7 volts, again for the 12 ohm resistor. And then finally for the 20 ohm, it's just 1/7 times 20. You get 20/7 volts. Okay, so we have all the voltages, we have all the currents. The only thing left to find is the power for the whole circuit. And there's 2 ways you can do that. The first thing you can do is you can find the power in each of these 3 resistors individually. That's the long way of doing it. And then you'd add them all together. That's the long way of doing it. The way faster way of doing it, if you want to find the power in the whole circuit, then all you need to do is look at the battery. This battery was 6 volts. The current going through it was 1/7 amps. If you want to find the total power in this circuit, just do V times I for the battery, and you'll get it immediately. Voltage is 6, current is 1/7. The power is 6/7, and the units are watts. And we're done. Easy. Any questions on number 29? Okay. Now for number 30. My advice for number 30, write small. This is a long one. Number 30, what is the voltage and current through the 12.5 ohm resistor? How much power does it draw? So notice we're only looking at the 12.5 ohm resistor. Technically, I could have looked at any of these resistors. I only said the 12.5 because I wanted to be able to do this problem on 1 page of work. But technically, I could have asked for any of these. But it doesn't matter. So the process stays the same. The first thing you need to do is combine these down to a single resistor. So I see these 3 resistors, they're in parallel. I'm going to add them in parallel first. Of course, I don't like adding them in parallel, but what are you going to do? So 1/R total is equal to 1/100 plus 1 over 100 plus 1 over 12.5. And as soon as I see that decimal there, I know I'm going to plug this in my calculator. I'm not getting a common denominator this time. So when I add these up all together, I get 0.1, okay? But that's 1 over R total. Now, how would I solve for R total then? I can't just flip it like I did before. Well, I'm going to raise both of these in my calculator to the negative first power. That's how you take the reciprocal in your calculator. And the total resistance is just going to be 10 ohms now for that little guy. It's going to be 10 ohms for all three of these resistors. Isn't that cool? When you add resistors in parallel, the total is smaller than even the smallest one before, which was the 12.5. And that will happen every time with parallel, which is neat. So now I'm going to redraw the circuit. So I've got a 50 volt power supply, I've got a 40 ohm resistor right here, and I've got a 10 ohm resistor right here. And isn't that cool? Because now I'm going to add these in series, the 40 and the 10, and we love adding resistors in series. So the total resistance is just going to be 50 because it's 40 plus 10. And now I've got a circuit with a single resistor, which was my goal from the beginning, 50 volts. 50 ohms. Ohm's law, we're going to like Ohm's law for this one. I'm telling you this right now. V equals I times R. Oh my God, this pen is killing me. V equals I times R. It's really not the pen, it's the software, but I will keep saying the pen. 50 equals the current I, which is what I'm solving for, times the resistance 50. And just divide by 50, the current is 1 amp. Okay, now that's not the answer to my question, but I do want to address something. Here's what we just found. The current right here through the battery is 1 amp. Since the 40 ohm is in series, that is also a current of 1 amp. These three branches are in parallel, they will not have 1 amp. Remember what we said before, the currents will sum. So they will add, these three currents will add to 1 amp. But then after they meet back up, they'll add back up to 1 amp down at the bottom. Okay, cool. So here's the problem. I don't know the voltage or the current right now through the 12.5 ohm resistor. And the reason why I don't know it yet is because I don't know this voltage right here. Look at this voltage right here. I don't know what it is. I don't. It's true. Because the voltage here, I need to erase some stuff so I can have room. The voltage right there where my black dot is, that voltage is 50 volts. And the reason why is because it's connected to the battery. Therefore, this end of the battery is going to be 0 volts. And so I have 50 volts, I have 0 volts. The only thing I don't know is the voltage right there. How can I find the voltage right there? Ohm's law, but for the 40 ohm resistor. I'm going to use Ohm's law just for that 40 ohm resistor. And here's what I'm going to do. Let me show you. This is one of those times where I like to use the delta. So this is a 40 ohm resistor. I know the current through the resistor is 1 amp. The voltage here is 50 volts. And the voltage here is what I'm solving for. And this is one of those where I say delta V equals I times R. Because this is not a zero case anymore, obviously. So the change is 50 minus V, where I'm solving for V. The current is 1 amp. The resistance is 40. Solving for V here, I can subtract 50 from both sides. So that means negative V equals 40 minus 50, so negative 10. The voltage is 10 volts. That voltage right here is 10 volts. Great. And the reason why this is great is because I have a conceptual question for you guys. Which resistor, the 100 ohm, this 100 ohm, or the 12.5 ohm, which resistor will have the highest voltage? Someone please tell me. Crickets. Okay, I will tell you. The answer is it's a trick question. They all have the same voltage. Why? Because they're all in parallel. And like we said earlier, when they're in parallel, all of them have the same voltage. The other reason I can prove that is because, hey, the voltage right here is 0 volts. The voltage right here is 0 volts. The voltage right here is 0 volts. It's the same everywhere on this wire. The only time the voltage ever changes is when you come across a resistor, like right here. So, for that reason, we get 10 volts for all of these. So the voltage is 10 volts. Excellent. And once I have the voltage and the 12.5, I can easily find the current. So here's the 12.5 ohm resistor. The voltage is 10 volts. V equals I times R. I don't care about the delta anymore because V is just 10. There's no subtraction going on. I times 12.5. I just need to divide both sides by 12.5. And the current is going to be 0.8 amps. And if I wanted to find the power is easy because the power is just the voltage times the current. So the voltage we said was 10. The current is 0.8. And so the total power is going to be 8 watts. And there we go. That's everything for number 30. Just a few more questions to go. We're almost done, everyone. On to number 31. Number 31, in the circuit below, find the currents I1 and I2. Note, they may be negative. And that's because I might have purposely drawn them going the wrong way. And that's fine. We'll deal with that when we get there. But the first thing I want to say is this is when you use KCL, when you have a problem just like this. And that's because you have two junctions you're going to look at, the first one there and the second one there. So I'll label them. I'll call this one junction 1, this one's junction 2. And so for the first one, I say I in equals I out. Which one's pointing in? Looks like the 4 amp is pointing in, so 4 is equal to the currents pointing out. The currents pointing out are the 6 amps and I1. So 6 plus I1. If I want to solve for I1, all I need to do is subtract 6. So that means I1 is equal to negative 2 amps. Now the fact that it's negative doesn't matter. I'm just going to circle negative 2 amps. That's right. Technically the current is pointing that way, but I'm just going to be consistent with my notation. I'm going to use negative 2 amps for I1. I'm going to keep I1 pointing to the right. I'm not going to touch it, and we're going to have a great time, and we're going to get the right answer. Okay, so for number 2, same thing. Current's pointing in. This time I1 is pointing in, and I2 is pointing in. So both of those are positive. And then equals the currents pointing out. The only current pointing out is the 9 amp. So equals positive 9. Now I1 was negative 2 plus I2 equals 9. And then if I just add 2 to both sides, I get my final current. I2 is just going to be 11 amps. And there we go. There's our answer. Not too bad. Any questions on number 31? Okay. Number 32, I made the mistake of making number 32 way too hard with the numbers. But I more care about the concepts than the algebra for this next one, just so you know. So for number 32, we want to write the KVL equations for loop I1 and loop I2, and then we're going to find I1 and I2. So we're going to have 2 loops. The first loop I1, second loop I2. Again, with KVL, I choose a starting point. I'm going to choose right there as my starting point because I like to choose right next to the battery. And so now what I'm going to say is, I'm going to say, again, the summation of all the voltages is equal to 0. The first thing I come across is my battery. Batteries are always positive, so I say 20 for the battery. The next thing I come across is this resistor right here. And since you subtract resistors. I'm subtracting IR. Here's the tricky part. I know the resistor. The resistor is 1K, which is 1,000, but the current is the tricky part. So if you look at this current, you've got a current I1 going down, and you've got a current I2 technically going up. Does everyone see that? Current I1 is going down at that resistor. Current I2 is going up. So then what's the current? Here's what the current is. It's going to look confusing, but just deal with me for a second. The current is going to be parenthesis I1 minus I2. And the reason why is because we're saying I1 is positive and I2 is negative. I2 is going the wrong way. And then the resistor, like we just said, is 1,000 ohms because it's a kilo ohm. And then after that, we finish the trail. We're back where we started, so that must equal 0. There is my first loop right here. So that's the first loop. For the second loop, this one's going to be, I think, easier. We'll see. Actually, no, it's harder. Who am I kidding? So let me erase everything I just drew because it's already too cluttered. So for this one, I2, again, I choose my starting point. I'll choose this point right here as my starting point. And again, I'm going to go around. I'm going to go around town. So the first one I come across is the 1 kilo ohm again. Look what happens this time. This time, I2 is going the right way, but I1 is going the wrong way. And remember that its resistors are always negative. There's no battery. Doesn't matter. I say negative, parenthesis, I2 is positive, minus I1 is negative. And again, the resistor there is 1,000 ohms. And again, there's a negative sign there. And the reason there's a negative sign there is because resistors, you always put the minus sign out in front, even though I know there's a second minus sign right there. Okay, now the next thing we come across is the 3 kilo ohm resistor. Notice for the 3 kilo ohm, there's only one current touching it. It's just I2. Finally, something that makes sense. So then minus current I2 times the resistance, which is 3,000. And that's equal to 0. Okay, now...
Is this still second loop? Sorry, is this still the second loop?
Yes, it is still the second loop.
Okay.
Okay, now we're done the second loop. I forgot to... Here, wait, hold on, there's a 0 here. Okay, so now we're done the first and second loop equations. This is all I care about for the problem. In other words, the math ended up being too hard. This is like a system of equations kind of problem. It takes a while to solve. So I'm just going to tell, like this is the important part of the question. I'm just going to tell you the answers. If you do it right, and you can do this on your own if you want, but this is just annoying, so I'm not going to waste time with it. I1, you get 0.0267 amps. And if you correctly solve for I2, you'll get 0.00667 amps. And again, what I care more about is the KVL equation, which is these right here. And I know, if anything, this is, I know, one of the hardest things to wrap your head around in this entire review. So if you do have any questions, please say them now, or forever hold your peace.
Could you scroll back down to the answers?
Yes.
Okay, thank you.
Yep. And now the last topic we have for tonight. Let's bring us home. We are looking at ammeters and voltmeters and then RC circuits. So ammeters look like this in a circuit. It's literally like a letter A in like a circle like this. And what they do is they measure current. And the reason why that makes sense is because what are the units for current? Well, they're amperes or amps. And so the ammeter is going to measure the current. And what you need to know about the ammeter is that they have a very low resistance. They have a very low resistance, like essentially 0 resistance. And because of that, would you put a ammeter in parallel or series with the circuit, you would place it in series. We would place the ammeter in series because it has a very low resistance. Now, voltmeters are going to be the exact opposite. The voltmeter measures voltage, obviously. It has a very high resistance, like essentially infinite, as far as we're concerned. And because of that, we would always place it in parallel. And that's everything we need to know about voltmeters and ammeters. Now, RC circuits. RC circuits look something like this. Let me just draw one real quick. You've got a little battery here. You've got a little like switch, you know, because you're going to turn the RC circuit on and off to charge and discharge. You're connected to a resistor, you're connected to a capacitor, and then you're connected back to the battery. Make sure your picture doesn't take up the whole box because we still need to write some equations here. By the way, the resistor and the capacitor, the order doesn't matter. You can put it vice versa, doesn't matter. But there's R and there's C. And what we're saying is you're closing the switch, like you're turning the circuit on with charging, okay? And the equation is VC, and we always care about the voltage in the capacitor for some reason. The voltage in the capacitor has an equation. It's V naught, where V naught is the original voltage in the battery, parenthesis 1 minus e to the negative t over tau. And then the question is, what's tau? Well, tau is your time constant. Tau is called a time constant, and all it is equal to the resistor times the capacitor. You just multiply those two numbers together. That's how you get the time constant. Okay. Now for discharging. Discharging is when the resistor and the capacitor are now just like no longer connected to the battery, and they're just like by themselves. Okay? In other words, it was already fully charged at one point. Now it's just these two buddies on their own. And what happens is, for a while, like if you were to look at this circuit normally, you should say no voltage source, nothing happens, no current. But here's the thing. The capacitor acts like a battery for at least like a short little bit. It's going to supply the juice, and it's going to give it some juice. It's going to supply some power, supply some current, but then it just runs out, just like your phone runs out of battery, essentially. And the equation for discharging is VC, voltage in the capacitor, is equal to V naught times e to the negative t over tau. So even though it's no longer connected to the battery, it's fully charged, we would say, with V naught, and that's why it holds the charge for at least a little bit. Any questions before we move on to number 33? Okay, number 33, very easy question. What is the reading on the voltmeter and the ammeter? So remember, a voltmeter just measures voltage, ammeter measures current. It looks like we're in the right configuration here because the voltmeter's in parallel, like we said, and the ammeter is in series, like we said. So what I'm going to tell you is it's as if they're not even there. It's as if they're not even there. I essentially have a 20 volt circuit connected to a 30K, which is 30,000 ohm resistor. And so it's like it's not even there. If I want to find the voltage across the resistor, that's easy because every single volt, all 20 volts, are going through the 30,000 ohm resistor. If you don't believe me, the voltage here is 20 volts. The voltage here is 0. So the total voltage is 20. So that means the voltmeter is going to get a reading of just 20 volts. Done. And then if I want to find the ammeter, I just need to use Ohm's law to find the current. V equals I times R. And the voltage is 20. Current's what I'm solving for. Resistor is 30,000. My calculator doesn't care though. It's going to plow right through that. And we're going to get a current of 6.67 times 10 to the minus fourth power. And the units for that is amps. And there's our voltage and there's our current values. Now, if you had more resistors, it's possible you have more resistors, but you essentially do it the exact same way. You honestly kind of ignore the ammeter and you ignore the voltmeter, and you just try and find the voltage and the current that they're talking about. There's actually really no difference between what we just did with the other DC circuits and this problem, so it's not bad at all. Okay, any questions? Okay, 34 and 35, two left, both not too difficult. In the RC circuit below, what is the time constant? When the switch changes from A to B, what will the voltage be in the capacitor after 10 seconds? So first let's find the time constant, which is tau just equals R times C. R is 5K, which is 5,000. And the capacitor is 3 millifarads. Remember, you have to divide that by 1,000. So 0.003 farads. And we're going to get a time constant value of 15. In case you're wondering about the units, it is seconds. The unit for the time constant is seconds. And now we want to find the voltage in this scenario when it switches from A to B. What will the voltage in the capacitor be after 10 seconds? The first thing we have to figure out, is this charging or discharging? Well, remember this. You're starting at position A, and position A is a charging position. Position A is charging because you're connected to the battery. But then we switch to position B, and position B is a discharging position. Why? Because you're no longer connected to the battery anymore. As a matter of fact, because there's this open gap right there, it's as if the 6-volt battery source isn't even there anymore. And so at point B, we are discharging, which means we are going to use the discharging equation, which isn't too bad at all. So what I'm going to write is, for discharging, we would say that voltage in the capacitor is equal to V naught e to the negative t over tau. So that means the voltage in the capacitor is equal to V naught. Remember, that's the original voltage. Even though it's not connected to the battery anymore, it was still fully charged at 6 volts, times e to the negative t is 10, and tau we found earlier. I think I have that backwards, actually. No, I don't. I'm good. So divided by 15. Now, all you need to do is plug this in your calculator. It's not that bad, as long as you know where the E button is. And you're going to get a voltage of 3.08 volts. So in other words, what this means in English, this RC circuit was connected to the battery for a long time. It was fully charged at 6 volts. Fully charged. After 10 seconds, we've now gone from 6 volts, we're down to 3.08 volts. And as time goes on, we're going to keep shrinking and keep shrinking and keep shrinking until we eventually get to 0 volts, because we're discharging. Any questions on that one? Okay, and now the final question of the night. And it's a good one. It's actually very similar to another one I saw from your equation, your practice exam your professor gave you. Number 35, you are designing an RC circuit to charge to 99% of the total voltage in 3 seconds. The voltage source is 12 volts and the resistor is 250 ohms. What capacitance should you use to achieve this? So the first thing I'll do is I'll draw a picture of this. So we got a battery connected to an RC circuit, which means it has a switch. It's got some resistor here, got some capacitor here. Again, the order doesn't matter. You can put the capacitor first if you really want to. We know the resistor is 250 ohms. We're solving for the capacitance. This is in a charging configuration, so we're going to connect the switch. We're charging. And that's going to affect what equation we use, obviously. And they tell us the voltage source is 12 volts. Great. Okay, so all I need to do here is consider the charging equation. Vc equals V naught times 1 minus e to the negative t over tau. And honestly, since we know tau is just RC, I'm just going to write RC right away because I know I'm going to need that eventually. Close parenthesis. So here's the thing. If we want to charge to 99% in a time of 3 seconds, then what that means is, what's my voltage on the capacitor? A lot of you will probably get stumped by this, but if we went 99% of the total's 12, right? So if I went 99% of the total, it's going to be 0.99 times 12. That's my voltage in the capacitor. 0.99 times 12 equals V naught, which is the original 12, times 1 minus e to the negative. The time here is 3 because they say they want us to charge it in 3 seconds. So 3 divided by resistor is 250, and C is what we're solving for. So now we're here. Notice that the 12s will cancel with each other. That's nice. And what we're left with is 0.99. That's funny. I've reached the end of... This is not intentional. I have 20 pages of like free work, you know, like whatever you call this, scrap paper. And we just literally reached the bottom of this. So this is amazing. And we're going to end at 10 o'clock. This is the best review I've ever hosted. Thank you all for joining me. So 0.99 equals now just 1 minus e to the negative 3 over 250c. And if I want to solve for c here, this is actually kind of pretty algebra intensive, but it's not that bad. The first thing I do is subtract 1. So now I have negative 0.01 equals negative e to the negative 3 over 250c. The negatives cancel with each other. That's nice. What the heck just happened? I'm not getting that back, am I? Okay, that's fine. This was 0.01 equals, now this is all positive. And if you want to solve for the c in your exponent, the only way you can do that is taking the natural log of both sides, because that's going to cancel the e out. And now what we're left with is the natural log of 0.01, which is negative 4.61, is equal to negative 3 divided by 250c. Again, the negatives canceled out twice in one problem. Isn't that cool? Now I'm just going to multiply both sides by 250c. So 250c times 4.61 is equal to 3. Divide both sides by 250. Divide both sides by 4.61. Our final answer is 0.0026 farads, which if you want to write that in nicer units, I would multiply by 1,000 to give me 2.6 millifarads. And there is my answer. Now you don't have to worry about the millifarad part. That part doesn't matter. What matters is the farads part, 0.0026. And there we go. That's it. So thank you all for attending this session today. I appreciate you all for coming. I will now edit this video and post it on YouTube. Should be out by about 11 o'clock. If you have any questions, please stick around so you can ask them. And best of luck on your exam on, I think it's Tuesday. So take care, everyone, and thank you all for coming. Bye-bye.